Okay, so today we're going to talk about the more about the concept of chemical energy. But let me review a few things that we talked about the last time. And again, I'm going to use the notepad here as a way to annotate and highlight some of the things I talk about on the PowerPoint. So the PowerPoint should be available on Blackboard. You can download it, and I'm going to follow along and annotate it and give you more information. So the key thing that we talked about the last time in chemical thermodynamics, in terms of chemical energy, was the first law of thermodynamics. And the first law of thermodynamics is that energy can be converted in various forms, and the change in energy of a system can be done in can be written in the following way. So generally, the change in the energy of a system is given by let's call it delta E is equal to the heat added to the system plus the work done on the system. Again, this is work done on the system. Or I could write this equivalently in terms of the heat added to the system minus the work done by the system. And I'm highlighting this, not that they're two different equations, but the difference is in how I go about calculating this quantity work. And I think we'll denote that as a W prime as work done by the system. And in both cases, and Q is the heat added to the system. So if I add heat, it's positive. If it's if I remove heat, it's negative, and so on. So and the way I like to emphasize this is that the change in the energy, delta meaning a change, is equal to Q. We'll leave Q defined in the following way: minus P delta V, and this is then the definition of the thermodynamic work. So delta V is a change in volume, and this is always true. P minus PdV. So I push in on the system, and this is the external pressure and the change in the volume. So and again, one of the key concepts in the first law of thermodynamics is that this E is a state function. Which means that it only depends upon the current configuration of the system. Now, when we talk about a gas or we talk about a chemical system, we might specify the energy as a function of energy, as maybe a function of the number of molecules in the system, the volume that they occupy, and the temperature, and that would be the energy of the system. Number of atoms in the system, the volume, or number of moles of the system, the volume, and the temperature of the system. And so that the change in the energy can represent the change in any one of these variables. I can change the volume, I can change the temperature, and so on. And if I were to write this out, if I were to ask myself, well, how much does the energy change as I change the temperature? You would have to define something that's called the heat capacity. At constant volume, and which we'll call CV, and CV in the most general case is going to be, I'll write it as the change in the energy of the system as I change the temperature of the system keeping the volume constant. Now I'm writing it out, and also I would keep the number of moles constant. This is the not changing the number of moles or the number of molecules in the system, and the volume, not changing the volume of the system. And this is an approximate, but of course, and since we're talking, if we want to talk about an infinitesimal change in the energy versus an infinitesimal change in the temperature, I would really want to write this out as something that would be like a derivative of the energy with respect to the temperature, keeping volume and number of atoms or molecules or moles constant in the system. And this is the correct. So I could write out that the differential change, so dE, meaning the infinitesimal change of this delta E, I could write out as something like a CV times dt minus the pressure times dV. Again, these are infinitesimal changes, and you could imagine this as being the delta that I would have if I were to make this a very, very small continuous change in the temperature or the volume of the system. And this is the proper, the statement of the first law of thermodynamics. The constant volume heat capacity is a constant. It's a function of temperature, dt. It's also a function of the volume and the number of moles, and the pressure of the system. And this is a state function because if you remember from taking calculus, if you remember how to do it, the simplest integral you probably remember how to do is simply this. If I were to have an integral from a to b of dx, we know what to do. This is simply x evaluated from b to a, and that's equal to b minus a, right? That's all that is. And so dx is an exact differential, and this is the final value, and that is the initial value. So I could easily say that dE, going from state A to state B, is simply E at state B minus the energy at state A. This doesn't depend upon how I happen to go from A to B, or B to A, final to initial. It simply says that it's the difference between. So this is then the delta E. It doesn't depend upon the path. It depends entirely upon the endpoints. Work and heat are not exact differentials. They depend upon how heat was added or how work was done on the system. For example, if I were to have make a plot of the volume of the system versus the applied pressure, and I ask myself, well, how much work is done in moving the system from here to here, say some volume initial to some volume final, and versus going from some pressure initial to some pressure final. Okay, how the work that I do, the work in going from an initial to final is going to be some sort of integral minus v, or excuse me, v initial, v final. Get rid of that little dot right here. The pressure dv. It's an integral that would look like this. Now this is the area that's underneath this curve. Okay, this represents the area. So it depends upon how I've chosen to do this particular pathway. I don't know what the function, this p function is. It could be a straight line. It could be something that goes like this. So I could have a pressure curve. Maybe it goes like this. I do something crazy like that, and the the area under this curve is all of this, right? This would be the work. The area underneath this curve is the work. Now, I get a different answer if I maybe decide, well, let's increase the pressure and then decrease the pressure. I can take different thermodynamic paths that take me from one volume to the final volume, one pressure to the final pressure. The energy to some final energy only depends upon those two endpoints, but the amount of work that I did, and consequently the amount of heat that I had to add or remove to the system, depends upon this particular crazy convoluted path that I choose to take. I could take something that maybe keeps the temperature constant. Maybe I take something that doesn't add heat. I can take all sorts of different kind of pathways, and I get different values of the area underneath this curve. Work is not a state function. It depends upon the pathway that you take. The heat is not a state function. It depends upon the pathway that you take. So that's an important concept to bear in mind in thinking about all of this. Now, the thermodynamic entropy, or thermodynamic energy, is really not a useful quantity for us in many scenarios, because if I look at this particular kind of a problem, there might be looking at the total energy might be useful for systems that have a change in the volume and a change in the temperature. But in general, most chemical reactions that we look at are done under conditions of constant pressure, and so we need to define a different kind of state function. And so the enthalpy is something that comes about. So the enthalpy is denoted as the letter H, and it's I'll write this as to follow along. H is equal to E plus PV. And you may wonder why are we doing this? It's almost like if you think about it, what we've done, energy itself, E, is equal to Q minus PV, in the way that I have written it out in a sense. Well, it's actually not quite this. I mean, really what we want to write is that dE, the change in the energy, is a dQ. I'll still write it as a dQ, minus a PdV. And it's actually this, I think, makes it a little clearer what's going on. This is the internal energy. So if I look at the differential of H, and I ask myself, what is dH? The change in the enthalpy of the system. Well, that's dE plus dPV. Okay. Well, again, applying it, I think it's a little clearer to simply apply what you know already from your calculus, and write this as dE plus. Well, remember the distributive law of taking a differential. P dV plus V dP. But dE is dQ minus PV, P dV plus P dV plus V dP. Now it looks like I did nothing, but you see I can cancel out these two terms. Those two terms cancel each other out, and so I'm left with a definition of the change in the enthalpy, the differential change in the enthalpy, that looks like the following: dQ plus the volume and the change in the pressure. Now the advantage of this particular form is that most of the time, for the most part, when we do a chemical reaction, we do so under conditions of constant pressure. So under the condition of constant pressure, under the conditions of constant pressure, dH, the enthalpy, is equal to the change in the heat. So this is really a change in the heat of the system at constant pressure. Now, and that's of course something that's observable. Now again, this is a state function. It only depends upon the initial and final. So it's a proper state function. It does not depend upon the pathway that's taken to go between the two different states of the system. And to put it into somewhat perspective, what enthalpy is, it's a measure of the energy that's required to accommodate the system. You have to, whenever you have a thermodynamic system, you have to create a space in the environment for the system. So you have to create a space at constant pressure in the environment for the actual system, and the enthalpy refers to that. And again, most of the time, when we're doing a chemical reaction, we're doing something under the constant pressure condition. Only pressure volume work is then allowed, P delta V, and this is in a sense the how I would calculate the change in the entropy. So it's the and relate this then to the change in the energy of the system. Now, you may wonder again, why are we doing this? And if you dig a little bit again into the mathematics of all of this, you realize that what we have in writing this out, again under the condition of constant pressure, I can write this out as dH is equal to dE minus PdV. Or if I want, I can write this as a change in the enthalpy is equal to the change in the energy minus pressure, constant pressure, delta V. Now, if you look at this and you think about it, this is like the point slope formula. What we're really doing is we're mapping the energy and onto a different function, but we're not losing any information in doing so. It's so the same amount of, and of course this is all at constant pressure. You can think of this as the like the point slope formula in many ways. This is it's what's called a Legendre transform. It's what is called in mathematics. So there's no difference in the energy content between these two, the two sides of the equation. However, it's a lot easier to measure the change in the heat, because this is just the Q at constant pressure. We'll put a P here to denote this at constant pressure heat. It's easy to measure that. It may not be so easy to measure this, but this is something that's easy to do. You can do this using basic calorimetry. So you measure the change in the temperature of the system, and if you know what's called the heat capacity, the constant temperature heat capacity of the system, we can calculate the heat. We can look at the heat. So again, this is writing down what I have before. The definition of the enthalpy is delta E plus P delta V. It's written in a differential form as a delta, if you wish, the D, but you can imagine that this delta really should be taken as an infinitesimal differential. And then using the distributed laws of calculus, you can distribute this delta P delta V plus V, or delta P, to distribute this delta properly. Okay? again, this is, again, looking at this change in PV caused by change in volume at constant pressure, and you can look at this. And the only work that comes about is this. This is actually not correct. This line is not correct. It's unfortunate that the book doesn't understand calculus apparently. Anyway, so that's what the enthalpy is. Again, I like to think about it as the energy that's required to accommodate the system, to create a space in the environment for the addition of the system. It takes energy to do that. And again, if I have a chemical reaction, if I have a chemical reaction, I can see that the delta E or the delta H is the enthalpy of the products minus the enthalpy of the reactants. Final minus initial, always. And that's again because I can write that H going from A to B, thermodynamic state A to thermodynamic state B, dH is simply final minus initial. Now, you may wonder, how do I calculate this? How do I get these enthalpies of all of this? I don't know this. And that's what we'll learn in a moment. So again, I can look at this in the following way. I can say that if delta H is positive, if delta H is positive, then the enthalpy of the products is greater than the enthalpy of the reactants, it requires heat to do this reaction. So, for example, if I have A plus B, and make a plot of the enthalpy, let's write here's let's make the enthalpy here, reactants here, and I have some sort of products here. A plus B, maybe this is C plus D. So I have the reaction A plus B goes to C plus D, some sort of generic chemical reaction like that. Delta, I have an enthalpy for A, and an enthalpy of B, an enthalpy of C, and an enthalpy of D, and importantly, I have an enthalpy for A plus B and an enthalpy for C plus D, and this is in the delta H. So I've gone from here to there, and so clearly heat added to the system. I had to put heat into the system. So in other words, if this reaction were to go on, I would be pulling heat out of the environment for this to go on, and this would be something that would be endothermic. This is an endothermic reaction. If I can have an exothermic reaction, delta H is less than 0, I could have something that might go A plus B to C plus D, requiring some sort of downward delta H. Heat would be liberated from the system, and this would be an exothermic reaction. Remembering our definition of exothermic and endothermic has from yesterday, or from my last lecture. Okay, so let's do an illustrative example for this. If I burn methane gas, let me look and see if there's any more data that we need to see. If I burn methane gas at constant pressure, so if I burn 1 mole of that methane gas at constant pressure, I liberate 890 kilojoules of energy. Okay? How much energy is released if I burn 5.8 grams of methane at constant pressure? So 1 mole of methane gas. Let's ask ourselves, how are we going to do this problem? Let's write this down. So I burn, so 1 mole Okay, if I combust that, liberates, this gives me 890 kilojoules per mole. So if you want the enthalpy of combustion, the delta H of combustion, let's write it out like that, of methane is equal to 890 kilojoules per mole. Okay. So now it becomes a simple problem. How many moles are in 5.8 grams of methane? So 5.8 grams of methane how many moles? Okay. Well, I need to figure that out. So I can look ahead. I'll simply look ahead, and you would use your periodic table to do this. We have the number of moles of methane that's burned. And this is equal to, you can see here, it's equal to 0.36 moles of methane. Okay, 16.04 grams per mole. And now I can easily determine the delta H of combustion. So the delta H of this combustion of this process is going to be the number of moles of this is, let's call this guy N, the number of moles times the delta H of combustion. And a lot of times depending upon the book and depending upon the notation that you might see different annotations around this. We might see something that has a little note like this, that this is now the molar and under standard conditions, but this is maybe a little bit too much detail that we need to deal with. We'll assume that these are all standard quantities and that this is now the delta H of combustion. So the delta H of combustion is equal to is equal to this, and of course he has this as a minus delta H here, and so therefore and the reason this is as a negative, 1 mole of this releases that much energy, so we need a negative. So I have a negative sign here corresponding to the fact that I've released 890 kilojoules per mole of combustion, and so this is going to be a negative quantity, and there we go. We can work out what that number is. 0.36 times 890, and that's equal to minus 320 kilojoules of energy has been released in doing this particular combustion reaction. Okay, let's go back one. Now, how do I actually measure this? So if I want to measure the heat measuring the heat flow or change is called calorimetry. It's called calorimetry. Now, again, the way I would want to look at this is, let's look back at the at our equation for the enthalpy, and what we find is, again, we can define a heat capacity, C, heat capacity, and it's going to be a heat capacity is always going to be the we'll call it C is equal to the change in the energy divided by the change in the temperature. But I have to be careful when I do that, because I can do this change at either constant temperature or constant pressure or constant volume. And I can have two different heat capacities. I can have the heat capacity at constant volume, which is equal to the delta E over delta T constant volume and keeping the number of moles constant. Or I can have a CP, constant pressure heat capacity, which is the delta H over delta T constant pressure. And of course I really want to write this as an exact, as a differential, and I write this as some sort of dE dt constant volume number of moles, and this is equal to the derivative of H with respect to the temperature, keeping the pressure constant, and again keeping the moles. Now the notation again here denotes I'm taking the derivative or the change of that quantity with regards to temperature, keeping these things constant. It's important because these are multidimensional functions, and I need to take the partial derivative, keeping everything else constant. So it's important to remember that these are probably the two very important definitions that we have. So consequently, again, I can write this as a dH is at constant pressure is equal to Cp dt at constant pressure, and so consequence. That's from this equation. Or if I want to write this, I can write this as delta H is equal to Cp, assuming that the heat capacity doesn't change over this temperature range, delta T for this quantity at constant pressure. Always remember, what am I holding constant? So what I need to know then is if I measure the change in the temperature of the system, and I assume that the heat capacity doesn't change, then I have a measure of the enthalpy of the system. How much enthalpy is changed versus the change in the temperature. Now, what is this heat capacity? What's called the specific heat. And the specific heat is similar to the heat capacity in the sense that it is the specific heat is the energy required, ER, let's write this, to raise the temperature 1 degree C. Okay? 1 gram So usually heat capacities can be expressed in terms of a molar heat capacity or a specific heat. If a molar heat capacity would be something like the energy required to raise 1 mole of that substance by a degree Celsius, or specifically, like you could have a molar heat capacity to is something, again, it's required. It's the change of a molar substance. So you might see it expressed in terms of molar quantities, or you might see it expressed in terms of a quantity, of a gram quantity. And again, you need to look at to see how things are defined in the table that you're using. Here's a list of different kinds of heat capacity. So you would usually see these in joules per mole C or joules per mole Kelvin. Remembering, of course, that a change of 1 degree Kelvin is equal to 1 degree Celsius change, and so these are the specific heat capacities of different substances. And you notice that they're different, and why they are different is an important thing to look at. Solids tend to have lower heat capacities than liquids, and so on. And the reason for this has to do with the number of degrees of freedom and the number of ways that energy can be divided amongst those degrees of freedom. And in a liquid, certainly has more degrees of freedom than a solid. A liquid can flow, you have rotations, and you have different kinds of motions of the water molecule that can accommodate more heat. It takes more energy to raise the temperature of a gram of water versus a gram of solid, of ice. And this is one of the reasons why metals heat up faster than liquids, and so on. And it's not a conductivity problem, it's simply a matter of how much energy do I need to put in to raise the temperature of carbon, mercury, iron, aluminum, water, or liquid water, or ice by 1 degree Kelvin. And again, these might be substances that numbers that you would have to look at a specific temperature, although we're not talking about that in this particular case. The specific heat capacity might and usually does depend upon the temperature of the system. And the specific heat is generally taken as a C sub P, constant pressure heat capacity, unless otherwise specified. Okay, now, so the experiment that, in the absence of normal or of the coronavirus outbreak, you would be doing an experiment something like this. This is what's called the coffee cup calorimeter. It's a very simple laboratory experiment. You take 2 styrofoam cups. Why 2 styrofoam cups? Is simply that you want to isolate what's inside from the environment. You don't want any heat to flow in or out of this system over the time scale of your experiment. You want to be able to capture as much of the information as you can without any heat flowing in or heat flowing out as you do this experiment. So you might do a calorimetry experiment where you take a thermometer, you put a known amount of substance and water or whatever that you're using in this vessel, cap it off, and over the course of the reaction you'll start off with an initial temperature and a final temperature. You know the volume, you know the heat capacity of the system, and you are looking at hopefully having no energy transferred by the stirring mechanism or any sort of energy leaving or entering the system. So you need to make sure this is well insulated so that you don't muck up the experiment. And you look at the change in the temperature of the thermometer as some sort of reaction occurs. Now sometimes you might have the system starting off at equilibrium, then you break or you do something to initiate the reaction inside of this, and you go on and you measure the temperature of the system. So so if we were to do a problem like this, if you look again, looking back at this experiment, this is under constant pressure. The styrofoam cover doesn't seal the system from changes in atmospheric pressure. The pressure of the atmosphere outside the system is the same as the air pressure inside the system. So everything is being done under conditions of constant pressure. So we can look at the delta H as a measure of the heat, the constant pressure heat being generated by this particular reaction. Now, let's look at this particular reaction. So in this particular case, we're going to take 50 milliliters of 1 molar hydrochloric acid, 25 degrees Celsius. Whenever you do an experiment like this, it's always important to note the temperature, because the heat capacity might depend upon the temperature. And generally heat capacities and specific heats are tabulated and under conditions of the temperature for which they are, or the temperature range for which they are valid. And it's simply that the heat capacity changes with the temperature. So 25 degrees Celsius is pretty close to the standard condition, and so we can use the data that's provided in the book, assuming that 25 degrees Celsius is the condition for which those specific heats are measured. Okay, so we do this experiment, and we mix it with 50 milliliters of base, sodium hydroxide, again, it's at 25 degrees Celsius, and I increase the temperature by 31.9 degrees Celsius upon mixing all of these things together. That's the net ionic reaction, is simply creating more water. And I'm doing this all at constant pressure. So ultimately, what we're looking at is the heat capacity to rise 100 milliliters of water by a certain amount of energy. So we need to look at there's some data that needs to be done. So let's go back here. I got a little bit ahead of myself. Okay, so the way we do this is very simple. We say that the energy that's released by this reaction, I need to know the specific heat capacity of the system, and the delta T. So the experiment that we did went from 25 degrees Celsius. This was my T initial, and I went and you observe this at the final temperature of 31.9 degrees Celsius. I have 100 milliliters of solutions. So in other words, I have 100 milliliters of water, or since this is water at 25 degrees Celsius, the density of water is 1 gram per milliliter. So let's say rho water. Or in other words, I have 100 grams of water. So now what do I need? I have my Q, the heat, is equal to the specific heat, S. We'll call this guy S, the specific heat, times the mass times the delta T. Specific heat this is the mass, and this is the delta change in temperature. Now, the specific heat of water is something which we don't know yet. And so what we do know the specific heat of water is for water is 4.18 joules per degree Celsius per gram. Okay, that's the specific heat of water. So it's 1 calorie, if you want. 1 little calorie is the specific heat of water. It's just the energy required to raise 1 milliliter of water by a degree Celsius is 1 calorie, or 4.18 joules. And so now we have everything that we need to throw all of this together. We have a delta T that was equal to 6.9. So delta T is 6.9 degrees Celsius. All right, let's take the difference between those two is 6.9 degrees Celsius, and now I can throw all of this stuff together. And this is, we can write this out properly, 4.18 joules per degree Celsius times grams. I have 100 grams, and I have a 6.9 degrees Celsius. You can see all my units cancel out nicely. Again, it's useful to keep track of the units. The C's cancel out, grams cancel out, and I'm only left with joules. And I can do this multiplication properly, and I have 2.9 times 10 cubed joules. Right? That's the amount of energy. So you know, we can also then calculate the number of ions that are consumed, and so on. Again, this is the stoichiometry part of that particular problem. But the key is, how do I go from the experimental observation, with the measurements that you would do in the experiment would be, you measured the delta T. In principle, you've measured the mass, because you can put that on a scale, and this is in the heat at constant pressure that was given off. So the system heated up. This is an exothermic process, and so on. So anyway, this was released, and so if I want, I could calculate the enthalpy per mole of this reaction in a very simple way. So the net ionic reaction that was going on was that H plus aqueous plus an OH minus aqueous was forming a water. Liquid, and what you would then do, and for this particular quantity, if I have 100 milliliters of water that was formed, I can go back and say, well, I had 5 times 10 to the minus 2 moles of hydrogen ions consumed. So I had 50 milliliters I started with, and I know that I have 1 mole of H plus per liter, because that's the molarity of the hydrochloric acid that I started off with, and therefore I have that many moles of H plus, and therefore I can calculate the enthalpy of this reaction per mole as minus 58 kilojoules per mole. So heat is liberated at, so as if when I do an acid-base reaction, I liberate 58 kilojoules per mole into the system. Heat is evolved, and this is one of the reasons why I think I mentioned to you earlier in this semester, always add acid to water, because heat is evolved. That's an awful lot of heat to give off. This could cause the temperature to increase to the point, at least locally, to increase to the point where you start getting some boiling of the water, and you could splash acid onto yourself if you're not careful. But anyway, so that's the thermodynamics of how I can use the thermodynamics to calculate the enthalpy change in a calorimetry experiment. Again, we can do these again, and it's worthwhile looking through these problems and working through these problems on your own. In this particular case, again, you have a solid that's formed. The key information in all of this is that you want to make sure that the calorimetry absorbs a negligible amount of heat. So this is always, so 4.18 joules per gram per degree Celsius is the heat capacity of water. So the assumption that we're making in all of this is that the largest contributor to the heat capacity of the solution is that of the water. This is the specific heat of water is 4.18 joules per degree Celsius per gram, and again, the final solution is that of water, because everything is done mostly as a water-based experiment. This is the density of water, and everything else will take to be negligible. And if we were to do a more careful experiment, we would not take those to be negligible. We would have to be very careful in the way we do this. But and in this, again, this particular case, what the observation was, we went from 25 degrees Celsius, which is considered to be the standard room temperature. Again, if you're doing this as an experiment, you would measure this. So this wouldn't be 25 degrees Celsius. It might be 25, it might be 23, it might be 20 something else, but it's roughly going to be this. But you would need to do that measurement for your own particular case. And likewise, you would need to very carefully measure out these quantities so that you would know how much you have. Okay. Now, again, there's a lot of data that goes into these kind of calculations, and it's important to know where all of these pieces of information go. So you have a change in the temperature. I'm going to have a reaction that goes on, and I need to calculate the delta H of them per mole of BaSO4. So the net reaction is going to be reaction to this to form BaSO4. This is the BaSO4 precipitates out of the solution, and I would then measure how much BaSO4. Presumably this is done in stoichiometric quantities. I have 1 mole of Ba and 1 mole of SO4 ions in the system. So presumably I would get 1 mole of BaSO4 at the end of this reaction. Okay, so here we go. There's our net reaction. This precipitates out as a solid, and I'm going to look at the delta H of this. So this is an exothermic reaction. The temperature is increased. The delta H is anticipated to be negative, and it better be negative at the end of the day. So again, there's an internal check. If the temperature increases, delta H is going to be a negative quantity. So always check. Make sure that if it's not negative, you made a sign error someplace. Okay, so we can do this. Again, this is straightforward at this point. I don't need to write all of this down on the paper. I encourage you to work through this again on your own. It's easy to calculate a delta T, 3.1 degrees Celsius in this particular case. The mass of the solution is simply the mass of 2 liters of water, which is 2 kilograms, and again, assuming that the density of water is 1 gram per milliliter, which is the density of water at standard conditions. Again, we can go through this. We calculate the delta H, and we can calculate the delta H per mole of this thing formed, because we formed a mole, and so we now can conclude this is the heat of formation of BaSO4 from this reaction is minus 26 kilojoules per mole. So again, this is an important part of that particular reaction. So how do I do this in a little bit more dramatic way? And this is an experiment that I believe you do in the physical chemistry course, and that is called bomb calorimetry, which has this great connotation because it really is a bomb, and you do need to be careful when you're doing this, because the way this particular experiment is done, you take a combustible quantity, you run a filament through this that ignites, and you fill this quantity full of oxygen, or perhaps air, usually oxygen. You make sure that this water out of here is well stirred, and I have a thermometer, and of course I'm insulated from the environment. So what's going to happen in this particular reaction is at constant volume, so we'll use a constant volume heat capacity, because it's a constant volume. The volume is this volume of this container, less that of the sample cup and less that of everything else, but it's the volume of this container. So we're going to cause a reaction that consumes oxygen in this, and we'll measure the heat that's generated in the following way. So heat is going to need to be added to the system over the course of the ignition. I add so many amps or watts of heat in the ignition process. That has to be taken into account. There will be a little explosion inside of this. Generally, things that are heated up in oxygen ignite and burn very rapidly, hopefully combust everything into this, taking the reaction to completion. Heat will be liberated, and you measure the change in temperature of this thermometer. Again, you want to make sure this is well stirred so that you capture all of the heat. Of course, now some other things that you'll need to know to do this experiment. You'll need to know the quantity of water that is in this, because so now what are we going to be measuring? So the heat capacity of water, the constant volume heat capacity of water, that is, will be proportional then, or it will be the key quantity. So the change in the energy of the system is going to be the heat given to this volume, which is then going to be the constant volume heat capacity times the change in the temperature of the system. And that will tell you the energy of this particular reaction. Now, again, I emphasize that this is probably not an experiment you're going to do in freshman chemistry or general chemistry, but you will do this if you were to do this in a calorimetry laboratory, and specifically if you want to know, well, how many, how do I determine the number of calories are in a food quantity? Well, this is exactly how this is done. They are combusting the whatever quantity is in this, and to go to a combustion product and excuse me, determine the energy of combustion of that particular quantity, and and again, the other variable that needs to be taken into account is the heat that's added due to this ignition. This is an input of heat, and I have an output of heat. So let's see how they do this in this particular case. So in this particular case, and so I guess in the interactive examples that they're giving you here, they're not taking into account the fact that you had to add a spark to the system to get it to go. Here I have methane gas in the in this bomb burning with oxygen, and I increase the temperature of by 7.3 degrees Celsius. If I have some hydrogen, I get a temperature increase by 14.3 degrees Celsius. Now the key is, okay, well, this is telling you the heat capacity of the bomb calorimeter. So this particular case is the heat capacity of the water itself, kilojoules per degree Celsius. Let's go back this way. So in the absence of this reaction, this entire object has a heat capacity, and you're measuring the change in the temperature of this entire volume of water. So in this particular case, we determined that beforehand. 11.3 kilojoules per degree Celsius is the heat capacity of that entire apparatus. Again, if you were to do this as an experiment, you would need to determine that, because it depends upon the amount of water and all the other kind of things that are inside of this calorimeter, and it's a very carefully done experiment. So what we need to do now is to calculate and compare the energies of combustion for hydrogen and methane gas. And so again, let's look for this. So here we had 1.5 grams of methane gave a delta T of 7.3 degrees. 1.15 grams of hydrogen gave a delta T of 14.3 degrees. I have a heat capacity of the calorimeter, and those are that's all the information that I need to know. How do we do this? Okay, let's just think about this. Okay, so I have the heat capacity of the calorimeter, and I have a delta T. So in each particular case, I can now calculate the delta H of the combustion. Again, is going to be something that's going to look like a C. In this case is really the heat capacity of the system. It's this heat capacity times delta T of each particular case. So again, this is the constant pressure heat capacity because of the calorimeter of the system. So CP, heat capacity of the calorimeter, is 11.3 kilojoules per degree Celsius. Okay, so if I could then write that delta H of methane combustion of methane is going to be this heat capacity, 11.3 kilojoules per degree Celsius, times the delta T for that particular case, which in this case is 7.3 degrees. And likewise, delta H for the hydrogen is going to be 11.3 degrees kilojoules per degree Celsius. Let's put degrees Celsius over there, C degrees over there. Sorry for that. This little thing should be on that side. Times 14.3 degrees Celsius. Okay, so again, I can pull out my calculator and do that easily enough. Where's my calculator? Oh, there's my calculator. So my vintage 1985 calculator here that still runs probably the same set of batteries. And what do we have? We have 11.3, enter 7.3, and I have that 8 right there, 8.2, 8, 2, that's 82.5 kilojoules per degree Celsius. And then the other one is going to be 11.3 and 14 is 162 kilojoules. Degree Celsius cancels out. Degree Celsius cancels out. Okay. And what do we do here? Oh yes, this is the so this is the energy, the total energy. When I want this per gram, okay, the energy released per gram, and now I divide this through by the number of grams that I have, and this is the so if I divide this through by the number of grams, this is the total. So if I want the delta H per gram, so delta H per gram, I need to take this as 82.5 or 83 divided by 1.5 grams, and I get that this is now the 55 kilojoules per gram of the system. Okay, so like an important quantity. If I wanted to know how much heat can I get out by burning 1 gram of methane, or sometimes I might have this as a per mole quantity. This is the total delta H, and this is now the delta H per gram of that particular system. And likewise with the other one, and this is actually sort of telling. You know, if you look at, we talk about the hydrogen economy, is that the energy that's released by 1.15 grams of hydrogen is 162 kilojoules. Okay, and then because hydrogen is so light, it's 141 kilojoules per gram. So methane, the heat of combustion of methane, okay, is 55 kilojoules per gram, whereas the heat of combustion of hydrogen is 141 kilojoules per gram. So in other words, you're getting more energy out of burning hydrogen than you do out of burning methane. And so this is one of the motivations for the hydrogen economy of carrying around compressed hydrogen and burning compressed hydrogen. People worry about this because as soon as we start talking about the hydrogen economy, visions of the Hindenburg disaster start appearing on the news. And let me just say that is not the case. Methane gas is probably far more explosive, just as explosive as hydrogen. And we carry around tanks of methane gas and propane all the time, and it's not nearly as it's just as explosive and just as dangerous if you're in an accident carrying methane as it is hydrogen. In fact, hydrogen doesn't really blow up. Most of the Hindenburg disaster was probably due to a thermite reaction caused by the use of aluminum on the outside of the balloon itself rather than the combustion of hydrogen. So it's not the hydrogen that blew up in the Hindenburg. It was really the aluminum covered butyl rubber on the outside of the airship itself. So anyway, so next time I'll talk about what's called Hess's law. Hess's law is going to be one of the most useful quantities for thermochemistry. It is the quantity that allows us to predict the heat of reaction, the heat of combustion, the heat of a reaction under, again, the conditions of constant pressure. But we'll use this, that we will talk about in our next video lecture. So anyway, stay safe, stay clean, wash your hands, and I will see you again when the University of Houston reopens. If I can figure out how to end this.